David Smith here with one more flipped classroom math video. 3 tips before we start. First, remember you can speed up the playback if that helps you get through the video faster. Just make sure you understand and keep up with your notes. Second, you can pause the video at any time to catch up with your notes or think about the topics. Lastly, you can turn on the captions and watch my words go by on the bottom of your screen. Today's video covers the topics that we went through in chapters 2 and chapters 9. And if you remember, in chapter 2 we did non-right triangle trigonometry. There's a bunch of things we did there. And then in chapter 9 we took a look at power functions and optimization. Okay, so first, in chapter 2, the first thing we did, I kind of grouped these together, is we used the sine rule and the cosine rule to find angles and sides in non-right triangles. And this is cool because we don't have to use SOHCAHTOA trigonometry. We can use this on any kind of triangle. So the way I set this up is we have this triangle here with the vertices or the angles denoted with uppercase letters, A, B, and C. And then the side lengths are lowercase letters. That the way the relationship is that the big angle A is across from little side A. So you can draw this triangle, and understanding how these relate is key to doing a correct plug-in step when you're solving for an angle or for a side. So let's take a look at the rules that we've got here. The sine rule is right here. It's A over sine A equals B over sine B equals C over sine C. There are ratios, and they're all equal to each other. Now, you can use these ratios to find either sides or angles. I haven't written this as a solution to an angle, but you just need to rearrange the equation and then take the inverse trig function to find an angle. The cosine rule is definitely more complicated, and that is a squared equals b squared plus c squared minus 2bc cosine a. Now the trick with that is to realize that to find a side, you need the opposite angle and the two sides that include that angle, okay? So if you want to find A, you need B and C and the angle of A. And that's indeed how this one is written. So it's two sides and the included angle are related to the opposite side. Now I notice that students who work on these occasionally confuse that relationship. Because you get problems, they're not labeled with the A, B's, and C's. All you get are some angles and some side measurements, and you have to figure out that, oh, I have these two sides in this angle, that means I can use the cosine rule to find that side. In fact, some of the problems won't tell you which rule to use. You have to analyze the triangle and figure out what you've got. Finally, we can solve the cosine rule for angle A. All I've done is rearrange this equation and solve for A, and that's the inverse cosine of b squared plus c squared minus a squared over 2bc. And it's the same relationship. To find this angle, I need these two sides and that side, and then I can find the included angle using that formula. So there's one trick to know for sure. If you're looking at a triangle and you're asked to find some stuff, if all you know are 3 sides, your only entry point is the cosine rule. In fact, it's this version of the cosine rule. There's no other way you can get in there. You'll have problems sometimes that will say, find all missing sides and angles. And your trick there is to figure out how to get into that triangle, start figuring things out so you can figure out the rest of the measurements. In addition to using the cosine rule and the sine rule to finding sides and angles in non-right triangles, we use the area of a triangle with sine formula, which I've reproduced here. That's area equals 1/2 BC sine A. And coming back to our diagram again, we have the area of this triangle is 1/2 times that side times the sine of the included angle. Now that's very similar to the requirements we need to use the cosine rule. So remember that. So basically, I can give you this side, and the angle between them, and you can calculate the area of that triangle with this formula. However, we can also make it slightly more difficult. I can give you the area of the triangle and ask you to find either side or the angle. And to find the angle, you'll have to end up doing the inverse sine function to find that. So again, being adept with this formula requires that you understand the formula, that you understand at its root, you need two sides and the included angle, and then you'll need to be able to plug area in and find the other unknown, whether it's a side or an angle. In addition to non-right triangle trigonometry, we also took a quick look at area of sectors of circles. And what a sector is just a portion of the circle's area that's described by an angle. So the area depends on how big or small of an angle we sweep out through the circle. The two variables in this formula are, yes, the angle itself and the radius of the circle. And that's really all you need to keep track of. And the way we do this is the area is theta over 360. Now let's pause for a second. Theta over 360 is just the fraction of the total area of the circle. So this formula is intuitive. It makes sense. Whatever that fraction is, it's going to give you the fraction of the total area. So check this out. It's theta over 360, the fraction, times pi r squared, which is just the total area. So that's pretty much what we do there. I like to consolidate this formula by just doing theta pi r squared over 360. That's a little bit more concise, a little bit easier to plug in. All right, let's take a look at a more complicated variation on finding sector area. So what we saw is we had several different triangles or several different figures where they asked us to find the area of this little shaded area. And that's kind of funny. There's really no formula for that area. But fortunately, we have a formula for the whole sector, and we have a formula for the area of this little triangle that's described by theta there. And the trick to remember is that this is also r. Both of these things are radii, and if we know theta and r, then we do know the area of that triangle. So the overall process here is we take the sector area, which is that, and we subtract the area of the triangle, which is this piece, and that gives us the area of the shaded region. So let's break that down. Sector area from the last board is just theta pi r squared over 360. So that gives us the whole sector. Now taking a look at this little triangle in here, we have our area formula, which is 1/2 BC sine A. B and C are both r, so I have 1/2 r squared, because just r times sine of theta, the angle that's between them. So if I know theta and r, then the area of the shaded region here is just this expression right there. And I know you did some problems like that in the homework. Now I realized that we got some pretty complicated problems in the sector area part of chapter 2. So I wanted to take a look at one of those just so that you can see that and that you're ready for it if you see it on our test. So here is a pentagon inscribed within a circle. We just say it's inside the circle. And we have theta. We have a bunch of thetas. We have 5 thetas going around. It's a regular pentagon, so each triangle that makes up the pentagon is identical. And then we have r. And so r are these radii that go out from the center to the edge of the circle. Again, we're being asked here to find the area of the shaded region. So the first critical thinking step here is to realize that really all we're doing is this same calculation we did just a minute ago, where we subtracted the triangle area from the sector area, but then we're multiplying that by 5 because we have 5 of those instances. So again, I'm going to do this problem without an r, just to show you the general formula that you could use then to work the problem out. So here we go. The shaded area is going to be 5 times the sector area minus the triangle area. So now all I got to do is do the same calc I did before. However, I need theta. Okay, so this time, I could just put theta in there, but we can figure out theta right now because we know that we have 5 angles. They're all the same. We have a total of 360. So theta is going to be 360 over 5, which is 72. This is a key step to figuring out this problem. If you get one on the test and you have an octagon in there or a nonagon or a hexagon, you're going to need to remember this trick to find that angle to solve the problem. If you can't do that, you're not going to be able to solve it. So you've got to remember that. Okay, so here's my plug-in step. I do 5 times the sector area, which is going to be theta, which we know is 72 pi r squared over 360. And then I'm going to subtract my triangle area, which is 1/2, again, r squared, because these two sides are both r. So that's the 1/2 BC, it's just 1/2 r times r, which is 1/2 r squared times sine of 72, which is our theta, which is our angle between our two sides that we know. So if I knew r, I could figure out that area right now. Now, I want you to pause the video. You can simplify this formula just a little bit more, and I love to do that. I love my formulae to be nice and concise. Okay, so what I noticed is there is an r squared on the top in both of these fractions. So I factored that out. So I have 5r squared times 72 pi over 360 minus sine 72 over 2. And that's a little bit quicker. And you know me, I like to make my expression as simple as possible before I pull out my calculator and do that calculation. So if I knew what r was, I'd be writing that number right there. And then I'd get my calculator out and I'd crunch my numbers. Actually, let's just do that. Let's just say, what if r is 7? Okay? Pause the video, put 7 in for r, and let's see what you get. All right, I did a plug-in step. It's not much. I just put a 7 in for my r. These things stayed the same. So when I crunch all those numbers, I get 37.4 units squared for the area of the shaded region going all the way around my pentagon. All right, let's take a look at chapter 9. Now, chapter 9 kind of mixed a few topics together. We took a look at cubic functions. These are functions with x cubed terms in them. And then we modeled situations with cubic functions. And then we kind of finished up with optimization, where we optimized with cubic or with quadratic functions. So let's take a look at cubic functions first. The most simple cubic function is just f of x equals x cubed. That's all you need to have a cubic function. It's just a cubic term. Now, fully expressed out with all the possible terms, we could have something like 2x to the third minus 6x squared plus 9x minus 11. So you can have up to 4 terms in your cubic function. Here's the general rule: ax cubed plus bx squared plus cx plus d. And really the only requirement is that a can't be 0. Like for this one, b, c, and d are 0. There's no term there. We just have a, and a is 1. You can't have a cubic function without an a being equal to something, negative or positive or a fraction or very large. Okay, let's take a look at 2 graphs of cubic functions, and then we'll talk about how you need to deal with them for test questions. Here is f of x cubed. This function is really straightforward. It passes through the origin. It has one x-intercept and one y-intercept, and they're both 0, 0. There are no local maxima or minima. This function just decreases this way, increases that way. There is no limit on the domain or the range. This function can grow as far as it needs to in the x and y direction, and it can shrink as far as it needs to in the x and y direction. Okay? Now, let's take a look at a different one. This one is a sketch of x to the third plus x squared minus 2x. And you'll notice that it definitely does some different things. We have a local max right there. We have a local min right there. Also, we have 3 x-intercepts. We have one here, we have one here, and we have one there. And we have only one y-intercept. That's right there at the origin, at the point 0, 0. So this function has a whole lot more to be said about it. And you might get a question that says, label or show or state any local maxima or minima and all intercepts. And you can see now that we have 1, 2, 3, 4, 5 points of interest on that function. Now, a word about domain and range and true maximum and true minimum. This function has the same limitations, which are none, as this function does. Ultimately, the domain and range includes all real numbers getting bigger and bigger in the x and y direction and getting smaller and smaller in the x and y direction. This max and this min are considered local maxima and minima, not ultimate ones, because the function does increase and decrease forever. So you have to that's a little bit of a subtle point in there. A trick question could be, does this function have a maximum? And your answer to that would be no. Okay. Now, a word about using your calculator and creating graphs. Your calculator is a great tool. Use it. That's what it's for. if you get a question that says sketch the graph, use your calculator, put the function in there, then sketch the graph into your test or your quiz. Now you want to do a good job of that graph. Don't just kind of swag it in there and mark some numbers on it. If it looks like this on your calculator, do your best to make it look like that on the page. You want to label all of your points of interest. So if it said show the local max and min, you're going to want to do that, like put that point near there. You're going to want to show your intercepts along there, and you're going to want to give us some idea of the scale on your axes. So perhaps these are your 1, 2, 3, 1, 2, 3, and so you might just put a 4 out there. That gives me enough to know that each tick mark is 1. Same thing on your vertical. If that's 5, you could put that in there on 5. Now, disclaimer, these marks aren't necessarily correct for these intercepts and these max and min. I just swagged that on there. But if that was correct, this graph would be nice and accurate. You want to label your function, put that on there, and give us the mathematical function that you have. And then, of course, if you're being super thorough, let's do x and y for your axes. So do a good job. Your calculator will show you a nice, accurate representation of that graph. Do your best to translate that onto the page in a way that is faithful to what you see on the calculator. A last word here. In this section, in chapter 9, manipulating and using your calculator to create good graphs using the trace function to find max, min, intercepts, things like that is essential. If you can't do that, you're going to struggle with these problems. So please, please, please get some extra help if you need it so you can use your fancy calculator tool to answer these questions. Then it's actually kind of easy. You just have to put the calculator in, put the function in the calculator, look at the result, transfer that result to the page, and you're good. All right, I want to explain an optimization problem in the context of a cubic function. And we did this problem. You've done a problem in the homework. Knowing the IB, they may give you another one of these on a test either at the end of this year or maybe at the end of your senior year. So you're going to want to be able to do this problem. Okay, so it's a pretty straightforward concept. We have a sheet of paper or a sheet of cardboard or maybe a sheet of metal, and we're trying to cut out corners, square corners, so we can fold the sides up and we can make a tray like this one. And so we cut out these squares from the corners that have side lengths of x. And so what that does is that ends up making the height of our tray x. And then we have a length. And the length here is the total length of the piece of the cardboard minus twice the x that we cut out. And it's the same for the width. The width is this total distance, but the width of the tray is going to be the width minus 2x. So we're going to have w minus 2x there, and we're going to have L minus 2x there. And so the volume of our tray, which is length times width times height, is going to be the x, which is our height, our length, which is L minus 2x, and our width, which is w minus 2x. Now in the problem, you've got numbers for w and for L. But for this, I just want to discuss the concepts and the result on the graph and how to interpret that. Okay, so to get our volume is a function of x. It's going to be height, which is our x right there, times our width, which is w minus 2x, times our length, which is L minus 2x. Now that's a cubic function. I have x showing up 3 times. If I were to expand this and write it as a cubic function in that form ax cubed plus bx squared and so on, it would be apparent that it's cubic. Now, you don't have to do that. You could just enter this in on your calculator. One thing we did notice on the calculator that you had to do this, which is kind of weird, and I think that was on the TI Inspire, that if you didn't put parentheses around the x term, it choked and threw an error message. So if you're doing that and you see that, then just go ahead and put a parentheses around that leading x, and that should fix that problem. Okay, now if you put this into the calculator, you're going to get some graph that looks like this, where you have volume on the vertical and you have x on the horizontal. And what that's showing us is that as we cut out bigger and bigger squares on the corner and make the height of our tray bigger and bigger, our volume increases to a point. This would be the max. So that would be the x value that maximizes volume. And then, of course, if you put that x value in the function, it's going to spit out the actual volume for the optimized situation. Now, as you start cutting more and more out of the corners, that box is getting really, really tall, but it's also getting really narrow. And so the volume starts decreasing all the way down to 0 here. Now, the graph is interesting. As a function, math just lets it go forever. It can go negative, it can go up to this max, it can go down. We have a local minimum here in the function, and then it turns around and comes back up and goes on up to infinity. So as a function, this graph is exactly right. For our problem, this is meaningless, as is these parts. And for the problem, the only relevant part of it, the only part that actually maps the reality of our box, is from here, from the origin up to the max, back down to a 0 volume. So the rest of this, again, is a mathematical valid function, but for our problem, it's irrelevant. It does not make sense. So sometimes with mathematics, you have to come to that understanding that you've graphed a function, but in terms of mapping reality, there's only a part of it. In fact, what we could say is we could say for x from 0, x is bigger than that, x is bigger than or less than whatever this value is, x2. And that would limit our result to just the part of the graph that's relevant for our problem. Now that you've watched the video, take a moment to write down any questions so you can bring them to our next class. Always remember, you can watch the video again to deepen your understanding. If you enjoyed the video, please click like and subscribe.